Okay, Organic Chemistry 2330. Here is Chapter 13, Part 2, Carboxylic Acids. Okay, so like the name suggests, carboxylic acids are acidic. Now, they're not strong acids, they are weak acids, partially due to the stabilization of the carboxylate ion, stabilizing that charge over a total of 3 atoms. Okay, so if we start to define it as a weak acid, let's look at the pKa of it real quick. Remember, strong acids have a pKa of 0 or less, and so things like HBr and HCl are below 0 and tend to have negative numbers. For our carboxylic acid, it's one of our most acidic um, organic compounds, and the fact that it does do this hydrogen bonding, and that hydrogen bonding allows it to stabilize over that 3 atom set. Okay, so but with this right here, we can actually change the acidity of this carboxylic acid by having electron withdrawing groups near the carbonyl carbon of the carboxylic acid. So for example, if we have a single chlorine atom here that is on the carbon adjacent to this carbonyl carbon here, we actually can change the acidity. It drops the pKa or increases the acidity of the system because it is inductively pulling electron density away from that carbonyl. When it pulls that electron density away from that carbonyl, it makes that anion easier to stabilize. Therefore, that proton comes off easier. When that proton comes off easier, it is more acidic, okay? So if a single electron withdrawing group on that carbon can increase the acidity by almost 2 points here, by adding a second electron withdrawing group, it reduces it again, making it even more acidic. And our pKa drops another time by adding a third electron withdrawing group here. We are almost to zero pKa. We're almost to a strong acid at this point, okay? Now, this effect is best when it's that first carbon next to the carboxylic acid, okay? Now, the effect diminishes as you go further and further away from that carboxylic acid. So if we look at the pKa of the just butanoic acid right here, it's about the same at 4.82. By adding a single chlorine in that adjacent carbon, we're going to drop it to 2.83, making it more acidic. If we move that chlorine 1 over, so we're not at the 2 position anymore, we're now at the 3 position here, we see less of an effect. We only drop from 4.82 to 3.98. And then if we move it 1 more carbon over to this 4 carbon here, we see almost no effect at all. There's so many bonds between that chlorine and that carboxylic acid, it has very little effect. So not only do electron withdrawing groups help increase acidity, it's the proximity to the carbonyl group that makes it more acidic. So the further away you get, the less effect it has. Okay, so being the fact that these are acids, they react well with bases. For example, carboxylic acids are soluble, even if they're insoluble in water, by reacting them with potassium hydroxide or sodium hydroxide or other strong bases, it will pull them into water and make them water soluble. Now, it doesn't have to be just hydroxide. Amines are basic enough by themselves to deprotonate the carboxylic acid, giving you an ammonium salt and giving you the carboxylic acid salt as well. This works a lot for a lot of the prescription drugs we do, benzocaine, etc., have these ammonium salts, creating our water-soluble portions of the system. Okay. So that being said, we can actually deprotonate the carboxylic acid with a very weak base. For example, sodium bicarbonate, which is a fairly weak base and only has 1 proton available to transfer here, can deprotonate a carboxylic acid. But when it does, it creates a compound called carbonic acid. Carbonic acid is CO2 and water kind of bound together. And so once you make that carbonic acid, it decomposes into CO2 and water. And if the CO2 is allowed to evaporate, it makes it an irreversible reaction. You've completely deprotonated it from the sodium bicarbonate, but then you've created water and the CO2 evaporates. And that's one good way to isolate a nice pure salt of a carboxylic acid. Okay, so one of the things about the acidity of the carboxylic acid is that you can use this acidity to help separate it from other compounds. For example, alcohols are not basic enough to be deprotonated by sodium hydroxide, but carboxylic acids are. So if you have a mixture of an alcohol and a carboxylic acid, you can separate them using that acidity to your advantage. For example, you can mix benzyl alcohol right here with um, uh, benzoic acid and dissolve them up into a nonpolar solvent like diethyl ether. They both dissolve in that. You can then extract that solution with base. Only the carboxylic acid will deprotonate and be pulled into the water layer. The other alcohol will not deprotonate and will stay in the organic layer. So once we have that organic layer separated, all we have to do is remove the ether, and we've separated out our alcohol from our system. But now that our carboxylic acid is in the water layer, if we acidify it to reprotonate it to give us our carboxylic acid, it'll crash out of solution as well, and then we can receive a pure portion of the carboxylic acid from that water solution.